So, welcome to lectures on engineering mathematics 2, and this is lecture number 4 on line integral. So, today we will cover here what are the smooth and piecewise smooth curves, and also we will be talking about the simple closed curves, and then finally we will introduce these line integrals in vector setting. So, what are the smooth curves? So, let this R t, x t, y t, z t, which we denote for the curve, and this R t possesses a continuous first order derivatives and nowhere 0. So, we will emphasize here, I mean later on we will explore that why this nowhere 0 is needed for the given values of t. So, for all values of t, this vector should be non-zero, and then the curve is known as smooth. So, there are two conditions here. The R t possesses continuous first order derivatives and they are now nowhere 0 at the same point, a given point t. Then the curve is known as smooth. In other words, we can also say that the space curve R t is smooth when these derivatives, so dx dt, dy dt and dz dt are continuous on the given interval a b, and they are not simultaneously 0. So, again there we have written nowhere 0, and now we have here that they are not simultaneously 0. That means, for a given t they all are not 0 altogether in the whole interval a b. So, this condition nowhere 0 ensures that the curve has no sharp corner or cusp. This we will explore in the next example. So, for instance, if you consider this R t as t square plus t square curve in 2 dimensions, and t varies from -1 to 1, and if we compute this dr over dt, that means the derivative of t square is 2 t, and then t cube is here 3 t square. So, we have this tangent vector 2 t I and 3 t square j, and if we compute this as t equal to 0. So, we see that this tangent vector is 0. So, the tangent vector should not be 0. The meaning is that at every point there should be a tangent vector which is a non-zero vector. So, this itself, when we are getting this 0, this indicates that the curve is non-smooth, and if we plot this curve t square and I and t cube j, then we see that there is a corner here at the origin, or when the t is equal to 0. So, there is a sharp turn in the curve, and therefore, this curve is not a smooth curve. What one should also note that this condition that dr over dt equal to 0 does not necessarily implies non-smoothness. So, what does that mean? However, that whenever we have not equal to 0, that means there is a tangent vector which is not a 0 vector, that always implies smoothness, but not the other way around, that dr over dt is 0 necessarily implies that there is a non-smoothness. Like in earlier example, dr dt was 0 and we have seen that the curve was non-smooth. But for instance, if we consider this curve here t cube plus t square j, and t varies from -1 to 1, and we compute dr over dt and evaluate this at t equal to 0, then we will observe that the value of this tangent vector is 0. And in this particular case, we will see that the curve is smooth. So, that we can observe clearly from the figure of this curve. If we draw a graph of this t square I plus t 6 j, then we see that the curve is smooth at all points, including this t equal to 0. So, what is happening here? So, we can have a different parameterization, and this was one parameterization. So, if we take a close look here, that the x t was t cube and this y t was t 6. So, these two implies that we have here that y equal to x square. So, this is a parabola, nothing else. The given curve written in this parametric form t q y plus t 6 j is a parabola. So, we can have several parameterization. For instance, the other parameterization we can have like x t, we will take t and then y t as t square. So, in that case this particular parameterization, if we just compute dr over dt, so the first component itself, since it is t, the derivative will be 1. So, we have 1 plus and I mean 1 I plus 2 t j at its derivative or the tangent vector, which is always non-zero whatever value of t we substitute there. So, what we learn here, that there could be a form, a parameterization of a given curve, which may tell us that the derivative of this r with respect to t is 0, the tangent vector is 0 at some point of t, but this does not necessarily implies that the curve is non-smooth. The curve can be smooth, like the example we have seen here. So, there is a term which we will be also using, that the piecewise smooth curve. So, if it is made up of a finite number of smooth curves, so we can have a finite number of smooth curves, and there are sharp corners, but these are made of from here to here the curve is smooth, again in this part the curve is smooth, and again in this part the curve is smooth. So, here we will call that this curve is piecewise smooth. This is not a smooth curve as a whole, but in pieces this curve is smooth. So, coming to the simple closed curve, another terminology which frequently used in vector calculus. So, a curve which does not intersect. So, the important point here is that which does not intersect itself anywhere, and the initial and the end points are the same. This is known as a simple closed curve. So, the closedness coming from the initial and the end points, because they are same, and the curve does not intersect itself, that is what we use this terminology simple. So, for instance, this curve does not intersect itself, and initial point and the end points are the same. So, that the curve is closed. So, this is a simple closed curve, an example of a simple closed curve. In this case, it is not a closed curve, because this initial point and the end points, they are different. So, this curve is simple, but it is not a closed curve. It is simple because it is not intersecting itself. For instance, here this curve is closed curve, but it intersects itself at this point, and hence this is not a simple. So, it is closed, but not simple. Okay, coming back to the main topic of today's lecture, that is the line integral. So, we will introduce here that what is what we call the line integrals in this vector setting. So, we have here, let us suppose, so this is a particular example, but one can generalize this for many other or any other vector field. So, let a force field F act on a particle which is displayed along a given curve C. So, we have a curve here, the C, and a particle is displaced along this curve here, the given curve. It is being displaced from this point A to, let us say, this point B. And we also assume that this vector T be the unit tangent vector at given point x I y j z x I y I z I. So, suppose this is the point x I y I z I, and then we will compute the total work done against this force field F to displace this particle from A to, for instance, B here. So, what we do, we will break this curve into small sectors, as we do always in the integral calculus. Also, the definition of the integral which we had discussed already. So, here on a small sub arc of length delta S I. So, we say that this is our small sub arc here of length delta S I. The work done will be the force into the displacement. So, the force, because suppose this is the force field acting in this direction. So, we will find that what component of this is acting along the tangent of this curve. So, for instance, here this is the tangent of the of the curve and the unit tangent vector we have defined by this t vector. So, we will compute the component by this. So, this is a projection of this f on this tangent, which is given by this f dot product with this tangent vector t. So, this is exactly the component of the force acting along the tangent at any point, and then if you want to get this work done. So, this is the force and then the displacement is this d s I along the arc. So, this is for one small arc, and if we add from this A to B all these small arcs and then let the length of this arc tends to 0 in that case. So, here I have just shown here that at any point we have the similar situation. So, again this f dot t will be acting along this tangent t. So, if we add all these work here, so the total work done we can compute by this summation here I to n and then this delta w I, and then we take this limit that the number of segments of this total curve is n, and if let n tending to infinity. So, then we will get exactly the work done along the arc, and this limit here we write as the integral over the curve C and this force f, the dot product t and the ds. ds is this element on the arc. So, now we will explore that how to evaluate this integral and what are the possibilities, different ways of evaluation. So, suppose this curve C is given by this vector function x t y t z t, and you note that we have already learned this, that the unit tangent vector we can express in terms of the derivative of this r. So, the derivative of r divided by its magnitude will give the unit tangent vector, and the ds, this arc length, we have also learnt in the very first lecture that the absolute value of this the magnitude of this r prime t will give and multiplied by dt, that is the element here, this ds we can express. This is, if you remember, this was just the square root of the x t whole square and plus y derivative t whole square and plus z derivative t whole square. So, this was already discussed there. So, we can compute this ds in terms of this derivative of r. So, this f dot t ds, that was the integrand there in this curve integral. So, f dot and the t we have substituted from there, r derivative divided by the magnitude of this r derivative, and then this ds is r derivative magnitude into dt. So, this will get cancelled and we will get here the f and the r derivative dt, which can be also written f dot dr, because dr dt what we have written this r prime t. So, here we can also write dr as r prime dt. Well, so the total work done we can express in this form of this curve integral, or we call line integral, f dot t, this is the unit tangent vector ds, and now we have seen that we can write as this f dot dr, or we can write as f dot r derivative and dt. So, this is the simplest form of the evaluation. What we will do, we will substitute in f this parametric form x t y t z t, and this r prime t will be evaluated, the dot product will be integrated over dt, the single integral which we have learnt, and the t will vary, for instance whatever t goes from a to b depending on the problem. So, let us continue now the evaluation part, that suppose this is the integral. So, there are two ways one can evaluate this. The one which we have just seen, that if this is the equation of the curve, and then we can evaluate this dr as dr dt dt, this we know already, and this curve integral can be evaluated with the help of this single integral. that in f, in the vector field, we will substitute those parametric form x t y t z t, and then dr dt will be evaluated. This dot product will be integrated over t, and this t varies from a to b. In component form, suppose this f has these three component f 1, f 2, f 3, and naturally x is or r is this x y z. So, what we can do, the dr will be dx dy dz, and in that case f dot dr can be evaluated. So, this product will be f 1 dx, f 2 dy, and f 3 dz. So, what we will observe in the examples, in some cases when the parametric equation is easily available or given in the problem, then we can apply this form here in the vector form, and when we have the Cartesian coordinate or in the component form it is given, then we can exactly do this integral dx dy dz, and we will observe in particular examples that how to evaluate when we use this component form or the vector form. So, suppose we have this problem, find the work done by this force. So, this is the force field given, we have the three components over the curve equation is also given, that is the parametric equation or the vector function of this one variable is given, t varies from 0 to 1. So, this will naturally come from this vector function, that when t is 0, then we are at this 0 0 0 point, when t is 1, we are at 1 point. So, we are our curve goes from this 0 0 0 to 1 1 1 along this given position vector. Okay, so, the solution naturally, when this the parametric form is given, we will use this vector form for evaluation of this work done. So, we need to evaluate dr over dt, which is easy. So, the partial derivative t with respect to 1, here the t square will be 2 t, t cube will be 3 t square, and then we have the f. When we substitute here this parametric form, that means this x is t, and then y t will be t square, and z t will be t cube. So, we can substitute there y minus x square. So, t square and then minus x square, that is t square. Again here we have z minus y square. So, the z is t cube and minus y square, that is t 4, and the third component we have x minus z square. So, the x is t and minus this z square, that is t power 6, the third component. So, here this cancel out and we have these two components, t cube minus t square and t minus t 6 for f, and when we take this dot product, the f dr dt, we will get this 2 t. So, 2 t, the jth component here will be multiplied by this one, t square minus t 4, and 3 t square will be multiplied by t minus t 6, which can be simplified, and we get this simple expression for in terms of t for f dot t. Now, we can integrate. So, f dot dr, that is the limit for the t goes from 0 to 1, and this is f dot dr dt, and over dt we can integrate this simple integration, the value will be coming 29 by 60. So, the second problem where we compute again this line integral f dot dr, where f is given as this function x square plus y square, the the first component, the second component is minus 2 x y, and in this case the C, the curve is the rectangle in the x y plane, which is bounded by y equal to 0, x is equal to a, x y is equal to b, and x is equal to 0. So, we can draw this easily, y equal to 0, this is the line, and then we have x is equal to a, this is the line here, and then we have y is equal to b line, and then x is equal to 0 line. So, having this, we will now evaluate this line integral along this boundary of this rectangle. So, f is given x square plus y square and then minus 2 x y. So, note that in this particular case, since we have given this rectangle in this Cartesian coordinate, that here y is 0, on this AB line x is a, and CB line y is b, and so on. This will be much easier if we write in the component form directly in xy form, not having the parametric form first and then convert it. That obviously we can do, but that will be much more difficult as compared to this, because this is very trivial now. So, f dot dr, that means the x square plus y square, that is the first component, will be dx, and then the minus 2 x y will be with dy. So, this line integral we will evaluate. So, there are 4 parts of the boundary. The first we will consider the along OA. So, what is special along OA? The y is 0, that is given there. So, y is 0, meaning the dy is 0 and x varies from 0 to a. So, this is the information available along this OA axis. So, along this OA we will evaluate this line integral f dot dr, that is here. So, the dy is 0. So, the second part will vanish, only the first one will survive, where we have x which is varying from 0 to a, and the y is 0. So, in this first integral what we will do, the y we will set to 0 and this term will go to 0. So, we will have just the x square dx term. We have the x square dx term, which can be evaluated, and then we will get this a cube by 3. Similarly, along this AB line, what we do, we have x is equal to a, we have this dx is equal to 0, because x is constant. So, naturally the dx will be 0. The y varies from this 0 to b in this case. So, again the same situation, in the given integral we will substitute x is equal to a, the dx will be 0 and the y will vary from 0 to b. So, our integral will be for y. So, this integral will become the limit of y 0 to b, and we have the dx 0. So, the first term will go to 0, the second we have minus 2 x y. So, 2 and x will be replaced by a and y dy. So, this integral again we can evaluate, that is minus a b square. The third one, when along we are moving along BC. So, along this BC here y is equal to b, that means dy is 0, there is no variation in y. So, the second term in our integral here will vanish, and we have x square plus this y square dx. So, x square and the y square, so since y is b there, so that will be b square, and then over dx, x varies from then a to 0. So, this we can also evaluate, the value will be minus a 3 by 3 plus a b square. Similarly, along this CO where x is 0, so the dx term will be 0 and the second term will be also 0, because in the second term we have this x, and since x is 0, the second term will also vanish and the first will vanish because we have dx there. So, in this case, so this integral is going to be 0. If we add all these 4 integrals, since here a cube by 3 is there, here minus a cube by 3 is there, minus 2 a b square, here also minus 2 a b square. So, the value we will get minus 2 a b square. There is another terminology used here, the line integral as circulation. So, that let this C be a oriented or the simple closed curve. So, we call this line integral, this is for the closed integral we usually use. So, such a line integral, the closed line integral is called the circulation of f around C. So, it has some physical meaning, of course, we are not going to the details of that. So, the problem 3 is find the circulation of f around C, where f is given by this and C is the curve, y is equal to x square, the parabola from 0 0 to 1 1, and then another curve y square is equal to x, another parabola from 1 1 to 0 0. So, we have this curve here given, which is made of these two parabolas, and the vector field f is given, and we want to get the circulation of f around C. That means, the line integral of this f along this curve C, the closed curve C. So, this is the curve given there. We have this parabola y is equal to x square, y is equal to x square, and we have there y square is equal to x another one. So, this varies from 0 0 to 1 1, and then getting back to 0 0 through the another parabola from 1 1 to 0 0. So, the solution, so we need to compute this f dot dr. F is given here. So, dr we will write in this dx dy form. So, this f dot dr we can have in this component form as 2x plus y square dx and so on. So, this line integral we can break into the two line integrals over the C1 path, that is f dot dr over C1, f dot dr over C2, and f dot dr is given by this component. So, in this case also we do not have to write the parametric equation, because there are two separate curves there, two different parabola. So, either way you have to convert both of them to different parametric curves, and then we can again evaluate each of these integral, that is fine, or directly, since the relation y is equal to x square is given. So, we can also compute without converting into the parametric form. So, f dot dr is given here, and then along OAB. So, we will go along this curve C1 where y is given as x square. So, we can use this relation to compute the relation between dy and dx. So, y is equal to x square means 2x dx is dy. So, in one of the two integrals which will appear here, because dx and dy, for instance, the dy we will convert to 2x dx and y will be used as x square. So, then everything will be converted to one variable. So, here the dx, the second also for for dy we have used 2x dx, and then x naturally goes from 0 to 1 in this case, and of course, the same integral. So, the 0 to 1 in the other one. So, here we have 2x plus x square, because y square is x 4. So, here 2x plus x 4. The second term we have 3y. So, 3 x square minus 4x, and then dy is written as 2x dx. So, this simple again one dimensional integral we can compute, the value is coming as 1 over 30. Along BDO, if we take this second path now to get back to the initial point, that is y square is equal to x. So, in this case we have dx is 2y dy. So, in this situation it is easy to replace this dx by 2y dy and x by y square. So, we will do so now. Everything will be converted into y. The values or the range for y will be 0 to 1 again, the minus sign, because we are coming from y is equal to 1 to 0. So, that is written here 0 to 1 with the minus sign. So, this we can also evaluate, the value will be coming as minus 5 by 3. So, if we add the two, finally, we have this value of the complete, the whole line integral, the closed line integral as minus 49 by 30. Well, so this is the another problem where we can evaluate this f dot dr, where f is given and the curve is also given as circle, x square plus y square is equal to 9. So, the parametric equation we can write down for the circle, because here the relation the x y will be much more complicated to write down in the form of the component, this line integrals, better to do the parametric equation. So, we know the parametric equation for the circle, x is equal to 3 cos t, y is equal to 3 sin t, and the t varies from 0 to 2 pi. So, we have the parametric equation of the curve, and then we know that f dot dr can be evaluated as f dot dr dt and then dt. So, this we have to now compute this f dot this dr dt term. So, here this f was given y I minus 2x. So, the y is like 3 sin t and minus this 2x is 6 cos t, and then dr dt we have to compute, because x is given as r is given 3 cos t I plus 3 sin t. So, r t is x I y j. So, 3 cos t I plus 3 sin t j. So, from here we will get the derivative put there. So, here minus like 3 sin t will come, and then in this place 3 cos t will come, and then the dot product. So, 3 and 3 we will get this 9 sin square t, and 6 3. So, 18 we will get as cos square t from here. So, this integral we can evaluate as this minus 9 and the sin square t and plus this 2 cos square t, which is sin square t plus cos square t, we can take as 1, and then we have cos square t left there, which can be written in terms of this cos 2 t, and then if we integrate this integral. So, we will get the value as minus 27 pi. So, these are the references used for preparing this lecture, and just to conclude. So, what we have learned this line integral of f on a given curve C. So, that can be either evaluated in the component wise as f1 dx, f2 dy, f3 dz, and we have seen several examples that how to do that. The second evaluation, if we know that the parametric equation is easy to get, then we can simply do so. So, the dot product of this f and dr over dt, and then we can integrate over t. So, that is another way of evaluating the line integral. So, thank you for your attention.